So let's start with our setGrid function. It's a little bit easier to understand. That's what we'll start with. We've done things like this in the past when we were doing other games. So we're going to create a function to clear screen and set up the grid. Okay, DF for a function defining our functions, setGrid. It has two parameters, start and goal, and then we're going to screen fill with black, basically clear the screen, and we're actually going to create the grid here. So we're going to say 4x in range 0 to window size, and again, we want the first item. We're going to say cell size. Okay, our step is going to be our cell size. Okay, and then we're going to say for y in range, we're going to say 0 to window size, the second thing in our tuple. In this case, it'll be exactly the same as our first thing because we have 500, but you can change this to whatever you want to. This code will work properly because we're using the settings here that we set up here as opposed to hard coding it. So cell size will be our step is here as well. And then we're going to create a rectangle based on pygame.rect. We need an X and a Y for our rectangle. And then we need a cell size for the size of the rectangle. All right, so then we're going to say pygame.draw to draw the rectangle, right? Screen, light, and then rect is what we're going to draw. We're going to draw it on the screen. The color is going to be white. The rect is what we're going to draw, this rect, and the border is just going to be 1, okay? All right, so now that we have that, we also need to set our start and our goal, right? What was sent over. So we're going to visually represent the start and end points by coloring them. Red is going to be start, blue is going to be our end. So say draw start and end points here, and again, we're going to say pygame.draw rect, then screen red. Okay, and now we need a tuple here, and inside of our tuple, we're going to say start. Get the first thing out of the start tuple, multiply it by the cell size, and then get the second thing out of the start tuple, and then start. Then get the first thing out of the tuple, and multiply it by cell size, and then cell size. Okay, and so you don't have to type all of that all over again. We're going to basically do the same thing for our goal, but we're going to change this from red to blue, and we're going to change this from start to goal. So we're going to get the tuple that we sent over to this function for goal, get the second item and the first item. Okay, so cell size. All right, okay, so that clears our screen and it creates a grid. Now, what we need to do now is actually create our A* search. Okay, so we're going to do that here above the function we just now created. Okay, so this is our main workhorse. Of course, the A* algorithm, as we discussed is great because it's efficient. That means it finds the shortest path quickly without checking every single square on our grid. That's like finding the quickest way home without going down every single road. So think about how you could possibly use this in your real life. Maybe you're planning a community event and you need to figure out the quickest route to pick up all the supplies. You could use A* to do something like that. Okay, so when we create this function, we are going to have 3 data structures that are going to be our main ways of keeping track of everything inside of it. We're going to have a frontier list, which is basically just our to-do list. We have the squares that we want to check in our frontier. Then we have the came from dictionary, which is going to keep track of how we got to each square. And so we can find our way back when we return the came from to the main loop. And then we get the cost so far dictionary, which is like counting steps. It's keeping track of how long it took us to reach each square. And as a quick reminder of how the A* algorithm works, I'm going to play this quick video.
A* utilizes 3 main numbers to calculate the best path. The g-cost finds the travel distance from the node to the start node. The h-cost is the opposite, in that it represents the estimated travel cost from the node to the target node. The h-cost is optimistic in nature, so it will either be spot on or it will underestimate the cost. It will never give a cheaper than possible value. Take this grid for example. The h-cost of this node is 3 because it's 3 nodes from the target. But if we put an obstacle in the way, making 3 moves to the target impossible, the h-cost remains the same, as it was only an optimistic assignment. So to iterate, the actual steps required from any node will always be equal or more than the estimated h-cost. The f-cost is equal to the g-cost plus the h-cost. The lower the f-cost, the more attractive it is as a pathfinding option. The goal is to simply choose the lowest f-cost over and over until we reach the target node. Okay, let's look at a few examples of A* in action. Alright, so I'll begin by placing my target here and we'll begin pathfinding. So as you can see, all the nodes have a g-cost of 1 as we are just 1 node away from our start, but the h-costs vary depending on how far away they are from the target. So first we'll find our lowest f-cost, so this will be 4, and we'll choose this. So we will now move to this node and we will check our surrounding targets again, and we'll choose the lowest f-cost again. And as you can see, g-cost is getting larger as we're moving away from our start position, but our h-cost is getting lower as we're getting closer to our target, and our f-cost will stay the same as we are just raising one number and lowering the other until we find our target.
Okay, so we are going to start with finding our function here. So A* search. Remember, we're going to send over the start tuple and the goal tuple when we call it. So those are the parameters. We called it from our game loop, or we called it inside of our game loop rather. So we're going to initialize our main data structures with starting points. Okay. First is going to be our frontier, as I mentioned, which is going to be all the nodes that we're looking at. And that's just going to be a list with tuples inside of it. So the first tuple is just going to be our starting point. We're going to have 0 for the priority and then our start, okay, as the location node. Okay. All right. So this is actually the list that we're going to use the heap queue module to keep a priority queue. Okay. So that'll be our frontier. Then we're going to say came from, and this will be our dictionary, which is how we figure out where we came from. Okay. So start is going to be none. Okay. Okay. Remember, start is a tuple. So inside of this, when we randomly generated start inside of the game loop, it's randomly generated as a tuple with 2 numbers. So in memory, this will be the key. This is the first key value pair inside of our dictionary. It'll be a tuple, will be the key, and then the value is none, because this is where we start, so it doesn't come from anywhere. But as we add to this dictionary, we'll have key value pairs with the cell and then where it came from. So the next thing that's added to this list will have start as its value, whatever cell it might be. So the cell would be over here, and then start would be where it came from, or whatever this tuple will be when we generate the numbers. Okay. Then we need to have our cost so far. So at the beginning, cost so far is nothing, right? So we're going to say costs so far, and this is going to be a dictionary as well. We will use start as the key, then start. So the cost so far is nothing. So again, the cost to reach each node, and then this is where each node was reached from, and this is the frontier, or the nodes to be checked, which we are saving a list, which is going to be converted into a heap. Okay. All right. So now we're going to do a while loop to basically search through the frontier. As long as there are places to visit or nodes in our to-do lists, we keep going. We're going to use a heap queue, heap pop, and it's going to be like asking what's the most important thing to do, because as I said, we're going to create a priority queue. It always gives us the square that's most promising to reach. And the reason it's going to do that is because inside of this loop, we're going to calculate the cost, as we saw in the video, and we're going to use that as the priority, the F cost specifically. All right, so we're going to say while frontier. So while this is true, while it has items inside of it, basically, we are going to remove the cell with the lowest F cost, or the priority, from the priority queue. All right, and to do that, we're going to say current cell that we're looking at, we're going to say heap queue dot heap pop, and we will say frontier as the item, and then what we want is the first thing from this popped off of this list. So we don't want what priority it is on the list, because remember, this is the entire item inside of the list. Each item inside of our list is a tuple. We don't want the priority in the list. What we want is the actual cell, which is right here. And for the first one, of course, is where we start. But as we go around this loop, it'll be whatever cell we're looking at. Okay. So we want the one. Okay. All right. So next we are going to basically color in the square that we're currently looking at as we're examining it. And also we're going to put a bit of a pause, like I said before, so that you can actually see it, because this would actually run so quickly that you wouldn't be able to see it. So I'm going to draw a rect onto the screen, and we're going to make this green. So the current square that we're looking at has the lowest F cost. So it's the current, I'm going to say 1 times cell size, and then current 0. Remember, we got the current from our list, our priority queue, okay, times cell size. So this is the one that we're examining right now, because it was the most attractive in our priority queue. When we're starting out, we're just starting out from the start. But as we're going through, you'll see that as this loop goes around, it's always going to be the thing that's the most promising based upon the score, or the cost that we put in. So we're going to do an update, and then we're going to see delay 100 again, so that it doesn't go too quickly. And we need to be able to break out of this. We're going to actually check to see if the current is equal to the goal. If this tuple is equal to whatever our goal is that we got sent over, then we can stop this loop. Okay, we can break out of it. All right, so next what we need to do is, based on the current cell that we're looking at, again, when we first start, it's just going to be the beginning cell. The current cell that we're going to look at, what we want to do is we want to look left, up, and down. Okay, and we're going to use variables dy and dx, which you'll see more in calculus. D basically just means change, so the change in x and y. So we're going to create a for loop to do that. So we're going to say dx dy in, and then we're going to give it a list, and in that list is going to be a bunch of tuples basically. So we're going to say 1, 2, 3, 4 tuples, and we're going to say 1, 0, 2 to move, 0, 2. So we're going to say 1, 0 to move right, then negative 1, comma 0 to move left, and then comma 1 to move up, and then 0, comma -1 to move down. All right, basically, we're going to check all the cells around the cell that is our priority. Again, while we're first starting out, it's just going to be the first cell to see whether or not we want to move to it. So we're going to say next cell is equal to current cell 0, and then we're going to do change in dx, comma current 1, and then the dy, change in dy. Okay, so first we're going to look at right, left, up, down, okay, when we go around this loop. So the first time next cell is going to be the cell to the right of the current, then it's going to be the left of the current, then up and down. So it's going to loop 4 times. All right, so we need to make sure that the cell that we're looking at isn't off of our grid. So we're going to create an if statement here. We're going to say f0 is less than or equal to next cell 0, and next cell 0 is less than our grid size, and 0 is less than or equal to next cell 1. You read this another way. You can say next cell 0 needs to be greater than or equal to 0 and less than the grid size. And next cell 1 needs to be greater than or equal to 0 and less than our grid size. Remember, these are tuples because these are coordinates in our grid, right? We just now created this tuple, the next cell tuple, from shifting, when we go around the loop the first time, shifting to the right, okay? So if any of these are off of our grid, this if statement won't run, okay? So we're only going to do this if we're on the grid. So we need to calculate the new costs. Each time we move to a new square, it costs us 1 step, and we add this to our total step count, which is kept in our cost so far dictionary. We keep track of this cost to calculate the cheapest path. So we're going to say new cost equals cost so far, and then so far, and then we're going to use current as the key, and then we're going to say +1 to calculate the cost to current, or the new cost rather. And then we need another if statement here. We are going to ask 2 questions, basically. We're going to say, we're asking, first, have we ever been to the square before? The square meaning the next cell. And then second, we want to see whether or not this way that we've calculated is any faster than the old way. So we're going to say F's next cell, not in costs so far. So we haven't been there if we haven't been there before. So if the answer to either one of those things are yes, or new cost is less than cost so far for next cell, then we are going to we need to update the cost so far. So we need to say update the cost and add the square to the frontier for exploration later on. Okay, remember our frontier is our heap that we're keeping, our priority cube. So we're going to say cost so far. We're going to use next cell as our key, and we need to save our new costs. Okay, now what we're going to do is calculate our priority for this cell specifically, next cell. And the way that we're going to do that is using our heuristic. And